Hello, everyone, and welcome. I am super excited to have you all here this afternoon or evening or morning, regardless of depending on where you're joining us around the world today. My name is Anna Volker, and I'm the coordinator of outreach for The Ohio State University's Department of Astronomy. And tonight, I'm very excited to be hosting our Interstellar monthly movie nights. If you would like to use our closed captioning services, we have live cart captioning available, which can be accessed by clicking on the closed caption button at the bottom of your screen. As always, we're also joined by an ASL interpreter today for today's panel. And I'm also joined by a group of wonderful panelists who will be discussing the science behind the film Interstellar. I have just now turned off the chat as this does interfere with the captions. So I instead encourage you to please use the Q&A function for any questions or comments you have throughout the webinar. And it's from the Q&A that I will be reading out questions out loud. If you'd like to ask a question verbally, you also have the option to click the raised hand icon and to be called on in that way. So without further ado, I'm going to go ahead and have each of our panelists introduce themselves to you all as the audience. I'll have each panelist just say your name, your position, what you work on, what you research, and how it relates to Interstellar. So what part of the movie are you most excited to discuss? So to start things off, I'll turn the floor over to Dr. Laura Lopez.
Hi, thank you, Anna. So I'm Professor Laura Lopez, and so I'm an assistant professor of astronomy at The Ohio State University. And my research is on the life cycle of stars, how they're born, and then once they exhaust their nuclear fuel, explode as supernovae. And that is also part of how black holes are born. And personally, I teach the black holes class for non-scientists at OSU, so I'm very interested to get into how black holes work and how wormholes work as well. Interstellar is a great example of this.
Amazing. Thank you so much. And next up, we have Dr. Christopher Harada.
Hi, I'm Chris Harada. I'm a professor in physics and astronomy at the Ohio State University. So my research is in cosmology, and that's the study of the structure and evolution of the universe. I'm interested in I'm interested in this panel specifically because in studying the universe as a whole, we use a lot of general relativity, the theory of gravity in which we describe space-time as curved. And so anything that relates to general relativity and how we might test it and how we might use it and how we might calculate things with it is of interest to me. And of course, that would include anything related to black holes.
Fantastic. Thank you so much, Dr. Harada. Next up, we have Dr. Samir Mathur. Oh, I believe you're on mute. Great.
Thank you. I'm Samir Mathur. I'm a professor in the physics department at Ohio State University. So I'm a theorist, and my interests are in trying to solve problems in quantum gravity, in particular, the kind of problems that were brought to us by Stephen Hawking. So in particular, in trying to solve those problems, I use the theory of quantum gravity, which is called string theory. And string theory then involves all the kinds of things which you might come across in Interstellar, the idea that there are extra dimensions, there are wormholes, of course, there are black holes. Can we travel in time? And all these questions actually automatically come to us. In spite of that, when I saw the movie, it was a little hard to understand. So then I actually went out and got myself this book where Kip Thorne actually explains what the science is behind the movie. And it's quite remarkable that, as he points out here, all the science is basically at least possible. May not be plausible, but all this is somehow based in correct physics, at least as stretched limits of what we do. So I actually found it very exciting.
Amazing. Thank you. And thank you for mentioning that book. I would definitely recommend folks, if after tonight you want to keep learning more, The Science of Interstellar by Kip Thorne is a great resource for people who really want to take that deep dive into the behind the scenes science of the interstellar universe. So thank you so much for sharing that. Next, we have Noah Gula.
Hi, everyone. I am a young professional. I am a graduate student and researcher in the Mechanical and Aerospace Engineering Department at The Ohio State University. Professionally, I've had experience as a propulsion engineer, actually designing rocket engines. And now at Ohio State, I'm performing additional research into nuclear thermal propulsion, which is basically an alternative way of how we can power a spacecraft. And it's particularly interesting for human spacecraft and spaceflight because it is possibly a really great enabling technology to allow us to get to Mars as soonest and most effectively.
Fantastic.
As far as Interstellar goes, maybe I alluded to it, but I'm really interested and was enjoy the imagination that Interstellar offers and of what human spaceflight can be in the future.
Thank you, Noah. Fantastic. And last but certainly not least, we have Jason Cervanic.
Hi, my name is Jason Cervanic. I'm the Education Outreach Director of the Bird, Polar, and Climate Research Center at Ohio State. I wear a few different hats in my job. One of them is to communicate science to the public, and usually that's cutting edge research the center's doing. The second is I have a number of research projects to communicate geosciences, usually through visualizations and virtual field trips. And the third, that is kind of the reason I'm here this evening, is educating the public about climate change, which is the number one reason my office gets calls, and helping decision makers sift through technical information in order to figure out fact and fiction. Full disclosure, until last week, I had not actually watched the movie, but I realized it was serious as soon as we downloaded it and rented it online and saw the length of it, that it wasn't just a typical 2-hour piece. They had actually gone longer, that I knew we were getting into something pretty deep. So I think the thing I enjoyed most is trying to challenge myself to apply the physics knowledge I had before they went ahead and explained stuff. And I felt like I was able to keep up pretty well. And I think also the depiction of climate change and the blight and how they didn't really treat it as a heroic response, but kind of an everyday, every person experience in response to that, which is how humans really deal with hazards like this, especially issues like climate change, which are going to be chronic. And so I just thought that was a really accurate way to depict what we see as challenges for the future.
Thank you. And I'd like to actually start off on that note because I have a number of climate change questions about the movie for you. But before I dive in, I just want to remind our audience that if you have a question at any time, you can just put it in the Q&A. And then once we get to a breaking period, I will start going through all the questions in the Q&A chat there. So be sure to let us know your questions as they come up, and we'll try to get through as many as possible before we reach 9 p.m. So Jason, starting with you, you mentioned climate change, and as anyone who's seen the movie knows, this is a pretty big part of the film. In the movie, it's described as this huge, irreversible thing where humanity's best bet is just to flee out through a wormhole. And the whole plot really is driven by how uninhabitable the Earth has become. So as a climate change specialist, is this a possible future for our Earth in real life? And what do we need to do to prevent that from happening?
I think there's been a number of depictions in cartoons recently of kind of the pandemic that's going on right now and kind of the economic tidal wave behind it. And then there's this massive tsunami, which is climate change, which is behind that. Right. So I think a lot of researchers in the community see the pandemic is really a way for us to think about how are we responding to these big issues that need collective action, that individual action is really necessary, but collective action. And I found working with decision makers, a lot of times when we think about adapting to climate change and they realize there's real costs, it's not a free lunch. You can't just do nothing and take it for free. But a lot of times those mitigation or reducing your greenhouse gases, which is what we have to do, is a lot less expensive and ends up harming fewer people. And so, for parts of the world that are developed, we have a lot more resources to throw at the problem, but we're also contributing disproportionately to the problem. And those populations in the US and around the world that least contributed to it are going to end up dealing with the biggest consequences of it. So there is kind of a justice issue that you even see kind of shown, depicted in the movie in some ways.
Yeah, thank you for bringing it up because I think that's a crucial part of climate change is the environmental justice aspect of it. And when we're talking about these consequences, one of the things that comes up in the movie is this reference to the blight that they talk about. And we have, as a result of this, we see these crop failures and dust storms that have just overtaken planet Earth. So are these realistic consequences of real life climate change?
Well, it's interesting because there was an article that came out last week that actually discussed about the prevalence of dust events being a concern in the future. For places like Ohio, we're far from the coast, so we don't maybe think about climate change impacting us, but it is already. These heavy downpour events we have that are going to be punctuated by dry spells is the signature of climate change in Ohio, a shifting rainfall pattern, and also warmer temperatures, specifically in the winter and at night. And even subtle changes, you don't think a degree or two matters, but I think in our own homes, we know changing our temperature a degree or two can drop our cost. But also we might have a significant other in our house that notices when that temperature has dropped 1 degree. And if you think of doing that over the entire planet, it has a big effect. We also know that climate change touches so many different issues. There's a wonderful depiction the World Economic Forum have that has like impact and risk and all the things in the top quadrant, that the 11 things that are up there. I think it's 7 or 8 of them, of the 11, are all touched by climate change. So even invasive species, if you think about the bark beetle out west, it has a longer growing season, it has more life cycles, and it has propensity to do more damage. So once an invasive species comes in, if it can have more life cycles near, it can spread more. And so even if climate change doesn't directly cause problems like that, it makes a lot of the problems we already face more magnified.
Interesting. Thank you. And one more question for you on this topic that was actually sent in by one of our students. She writes that early on in the movie, Cooper states, "We used to look up to the sky and wonder about our place in the stars. Now we just look down and worry about our place in the dirt." Interstellar has received renowned acclaim for its scientific accuracy, but some criticism for how it approaches climate change as a lost cause, implying humans can either leave the planet behind or remain and die. As an expert on climate change, what do you think of this presentation of the issue?
Yeah, I think in the climate change community, that's a message we don't want to convey, because it's not a either or choice. It's not a binary choice. There's a continuum here. So there's really bad effects and there's even worse. So the choices you make, and the sooner you make those choices, the more you can rein in the damage that's done, and the more windows of opportunity you have. The sooner you take action, the more that window that's open. And I think we want to leave people with a realistic sense of what the challenges they have to overcome, especially the next generation that's going to face a longer life dealing with these, but leave it on a hopeful message, because there's a lot of immediate things that could be done if we decided to accept the science and then look at the decisions that stem from that, as opposed to just having arguments over whether the science is accurate, which has really been settled in the research community 30 some plus years ago.
Right, right. Thank you so much. Awesome. So I'm going to transition here to our wormholes, black holes topic, and I'm going to throw that to Dr. Laura Lopez to kick things off for us, because this obviously is really crucial to the plot of the film. So at one point in the movie, a wormhole is explained by folding a piece of paper over and sticking a pencil through it. Is that accurate?
Yes, that's a great question. I think it's a really good analogy for a wormhole. So a wormhole connects 2 points in space-time, and you can think of space-time as a sheet of paper, and we live on that sheet of paper. And if we want to go anywhere else in space, we have to travel on that piece of paper. However, if we want a shorter way to get there, then what we can do is try to connect 2 sheets of paper with a tunnel through them, that is, tear a hole in the space-time, get that pencil through, and go to the other side. And in this case, the path would be much shorter, and you could get somewhere much more quickly than you would otherwise. So it's a really good analogy, but it's very unclear how one should actually tear space-time and put that pencil through to make the wormhole.
Right. And that leads into my next question, which goes back to in the movie, how Cooper states that wormholes are not naturally occurring phenomena. So do they really exist in real life? And if so, could they be human-made?
Yeah, so it's really interesting because wormholes are technically allowed in general relativity. It is a possible solution for Einstein's field equations. However, nature does not make wormholes that are naturally traversable, by which I mean that we can fit a whole spaceship through them. Naturally occurring wormholes are not stable, and they close off as soon as they are opened, or they are very small. So we think that there could be wormholes in the quantum fluctuation of space-time itself. But these are really tiny, like the tiniest possible scales. And so if someone, an advanced civilization, wanted to make a wormhole, they would have to take these tiny, tiny ones and expand it somehow and then hold it open, which would require this exotic material that would basically keep the walls from closing. So it is interesting that they are allowed, and it's just a matter of keeping them open that is the challenge, and making them big enough to let us get through with our spaceships.
Fascinating. Thank you so much. And so when we're looking at the wormhole in the movie, they need to reach one that's near Saturn. And so could you tell us, how would a wormhole there affect the gravity of that region? And would we here on Earth be able to detect it, in that area near the planet Saturn?
Yeah, so generally that wormhole, because of its curved space-time, is going to bend light around it. And that produces light in an observable ring or circle around the wormhole itself. And in addition, light from the other side of the wormhole that is looking through the tunnel, you'll actually see the part of space that's on the other side, the area around Gargantua in this case. And so in Interstellar, they're able to see this ring of light near Saturn that appears, and they're able to see it with the best telescopes. And so that's how they find out that it is there. So it is observable when it appears.
Thank you. And one of the questions I see in the chat that I want to answer now, since it's relevant to what you're discussing, Adrian asks, is what Dr. Lopez is discussing the same as the idea of the tesseract in A Wrinkle in Time? I don't know if you can respond to that. It's a pretty specific question, but is that at all related to A Wrinkle in Time, if you've read that book or seen that movie?
I haven't read A Wrinkle of Time in a very long time, so I'll need a bit of a recap to answer that question.
Gotcha. Well, maybe Adrian, you can give us another comment and let us know more detail on what you're asking, and we'll circle back. So one more question for you, Dr. Lopez. In the movie, black holes are described as oysters and singularities as the pearl. Can you tell us what that means and, really what is a singularity in the first place?
Yeah. So in general, black holes sort of have two main areas, so to speak. You have an event horizon, which is the place that defines the size of the oyster in this analogy. It's the place where inside of it, nothing, not even light, can escape. And the radius where the event horizon is determined by the mass of the black hole. The bigger the mass, the bigger the event horizon is. But then inside of that event horizon at the center is the singularity, which is a single point that is infinitely small, where the black hole's mass is located and where everything falls in and goes. And so generally, as you fall in, there's a lot of stretching and squishing that occurs, and which is what is happening to Cooper in the movie. Before he's sort of overcome by the singularity, that's when he's pulled into the tesseract, which is part of the question that was asked previously. And so the tesseract seems to be a separate area before he reaches that singularity that he's pulled into. And it's sort of a hypercube. It's a 4-dimensional or 5-dimensional space. And I didn't look into the science of that too much. Maybe the other panelists can talk about it. But it's a very interesting construction.
I think that's a great note to go over to Dr. Mathur to see. I'd love to hear your thoughts on that, because I think that people look at the end of the movie and think that maybe is the furthest we're really departing from reality. So can you speak to that in kind of the physics or lack thereof of the conclusion of the film?
Right. The end of the movie was really rather fast. So when I was actually seeing the movie, it was a little hard to understand what's going on. But then actually reading this book, which I was just mentioning, I understood a little bit more. And from what I understand, this is the basic idea they wanted to convey. They somehow want to have the idea that it is just us who in the future, when we are much more developed, actually come back and help us in the present to develop the new technology, which will help us to escape Earth and survive. But of course, going back in time is something that science fiction people have talked about for a long time. But if you just look at general relativity per se, you can't actually go back in time. So how do we do this? And so the twist they have on this is the following. We normally live in 3 space and 1 time dimension. So let's just say 3 space dimensions. And of course, there is time. But suppose there was an extra dimension. So there were 4 space dimensions and time. Then we can't actually see all the 4 dimensions. We only can move in 3 space dimensions. But suppose somebody was able to pull us out of these 3 and take us into the 4th dimension a little bit. And then when we travel to this, which they call the bulk, now all 4 dimensions, if somebody helped us to get there, then we could actually come back to our three-dimensional space, but at an earlier time. Okay, so the question is, who's going to pull us out there? And it's again our future beings. They are the people who are always invisible. We don't actually see them, but they have now learned to live in all these four space dimensions. So they make this tesseract a hypercube. A cube is just like a square is in 2 dimensions, a cube is in 3 dimensions. So hypercube or tesseract is a cube in 4 dimensions. Okay, so to take this cube in 4 dimensions, and they use this to pull Cooper out from the 3-dimensional world he is in a little bit into the 4th dimension. And then what's the advantage of going to the 4th dimension? The picture they're envisaging is again something that has come up before in the area of string theory. And the idea is like this. If your 3 dimensions are like this, and suppose 2 points on the 3-dimensional space are 1,000,000 miles from each other. If I go a little bit up in the extra dimension, this 4th dimension, the distance between those points may be only 1 mile. Okay, so if somebody pulls me up into the 4th dimension, then I can take a shortcut and immediately come back. So Cooper was really in a very far away place, but then these people pull him in using the tesseract a bit into the extra dimension, and then he can come back and just land up very quickly back into the place on Earth where he wanted to be. And the same idea of using the tesseract in the extra dimension also allows these beings who now know how to live in all 4 dimensions to actually come back right to the past. And at the time the movie starts, and at the time the movie starts, there are some nice little dust pattern and some signals which are looking like ghosts being seen by the daughter of Cooper. And that actually was Cooper himself sending those signals, having gone to the future, come back and is trying to give some hints. So we learned all that at the end, but the whole idea of time travel and the extra dimensions is all brought in together, because if we just have 3 dimensions, then normally people believe we cannot go backwards in time. So I don't know if that helps at all.
It does. Well, even the fact that you mentioned that you too were confused, that helps me personally, because if a black holes expert can watch it and still have confusion, I think that makes the rest of us feel better. So that's helpful for me to know. Speaking of black holes, though, I do want to respond to a question we have from Lindsay, who wants to know, do black holes really look like that? And we're referring to, this picture I have behind me, where we have basically these 2 planes of this really, really bright stuff. So could you talk a little bit about that and how realistic this is?
Okay, so let me say a couple of things. Firstly, this picture, which is the well-known picture of a black hole, is actually not a picture of a black hole. So the reason it's not a picture of a black hole is that what we call the black hole is what's the inside of the black hole. And that's normally the question of interest to theoretical physicists. Like once you go inside what Laura had called the horizon, what is in there? Is there a singularity there? And so on. But actually, once you're inside the black hole, then light cannot actually emerge to us and come to us. So we can't actually see the inside of a black hole. So what are we actually seeing in pictures like this? So what is happening is there is some kind of a stuff, hot gas, making an accretion disk going around the black hole. And it's a little bit far from the horizon. So it's about 3 times the radius of the horizon out and then further out. And then if you take some light from there, it sort of bends over the black hole by the gravity of the black hole and comes to us, but never actually having gone inside and come out. So we're not actually seeing the inside of the black hole. We are seeing the gas surrounding it, but we are seeing it somewhat distorted because the light from that gas is going to sort of bend around the hole and come back. Any light that goes into the black hole doesn't come out, but the one that goes just above, that will sort of bend around the surface, just not fall in, graze the edge of this place, the maximum place from which it wouldn't fall in, and come to us. And so that's what gives us this ring kind of shape. Like it depends on how the black hole is spinning, depends on the shape of the disk behind it, and all the gravity of the black hole, and that determines what you're seeing. So what you're really seeing is the part of the gas, which is part of the accretion disk, which is hot gas orbiting the black hole, which is behind the black hole. That light is curving over the black hole and coming to us. Okay, so that's interesting, but that's not actually what's inside the black hole.
And so would you only see this accretion disk of hot gas and matter if the black hole is feeding and growing, or is that there all the time?
So a black hole doesn't have to have this gas around it, and some don't, but many of them do. And when the gas is there, it is slowly falling into the black hole. So the black hole is accreting. And in fact, when the gas falls in, it gets very hot, it emits a lot of light, and this gives rise to these quasars, which are the brightest objects in the universe, and you can see them all the way to the other edge of the universe. They're the way for us to see really distant parts of the universe. So indeed, If there is gas around the black hole, it does fall in, it does get hot, but there doesn't have to be gas around the black hole.
Interesting. Thank you so much. So I am going to move now to Noah to talk a little bit more about the spaceships and the propulsion side of things. So Noah, one of the things that was interesting to me was that the characters in the movie, despite being in the distant future, are often maneuvering these spacecrafts manually and often with joysticks. Are spacecrafts actually controlled this way, or would AI be really doing most of the work for space pilots?
That's a really interesting question, and I hope everyone had a chance to see the really great space mission that just occurred on Sunday and Monday, where SpaceX brought some humans up to the International Space Station. And if you look closely, the astronauts there, they actually had touch screens in front of them, and they were able to control and manipulate the spacecraft that way. But in a more historical context, spacecraft for a long time actually had been piloted by humans with joysticks, because for the most part, astronauts who were piloting spacecraft were previously pilots flying aircraft, which also used joysticks. The Soyuz, the Russian spacecraft, which brought humans to and from the space station for about the previous 10 years since the shuttle used joysticks, but we're now seeing the emergence of newer technology and touchscreens.
Yeah, I'm glad you mentioned the recent flight, because this reemergence of flights to the International Space Station from the US, I think, is a really exciting thing that's been captivating the public lately. So I'm excited that you brought that up. Another question I had for you is about the Endurance spacecraft, which in the movie was a ship built by NASA carrying 5,000 frozen human embryos to colonize a habitable planet. And in the film, it's portrayed as this self-sufficient vehicle that travels for several decades and can contain this technology that's capable of putting humans into this cryo sleep for these long stretches of time. So I'm wondering, are we currently working towards any technology like this in real life? And just how far away are we from this type of spacecraft and the galactic tech that we see featured in this film?
Well, those are certainly really great challenges that we need to better understand if we want to continue our exploration in space, especially with humans. I'm not sure I can really speak to how realistic cryo chambers are, but certainly the effects of being in space for a long time is something that's on the minds of engineers today, and especially with regard to trying to get humans to Mars. Just this summer, I think there are 3 different spacecraft and robots which are on their ways to the Red Planet, and it's taking them until February to actually get there. And so if you're just a human sitting in the spacecraft, that's a long time that you're being exposed to radiation and to other detrimental effects like microgravity. So these technologies which allow us to have long-term sustainment in space are really important. Currently we address these with the International Space Station. Some of the record length stays up there on the order of like a year that an astronaut has been full 12 months or more. But even with those missions, we have hundreds of people on the ground supporting them, and we have to deliver cargo, multiple times a year so that they have a continued supply of food. And so for these long-term human spacecraft missions, like we're gonna need these kind of technologies to enable sustainment independent from the Earth.
Right. Thank you. And one final question I have for you, Noah, just came in from one of our attendees, Chris, who wants to know, what's the reality of the spinning habitat used in the ship? Could you speak to that?
So the reality of a spinning habitat, could you expand on your question maybe?
Yeah, so question asker, if you can tell us a little more what you mean. It could be referring to, I know in a lot of films they do like spinning to create artificial gravity. So I think maybe that could be part of what's being referenced. So this idea of, creating artificial gravity within a ship by spinning, possibly. But question asker, if you'd like to clarify that for us, that would be great. And in the meantime, Noah, if we want to wait for more clarification there. Oh yeah, it does look like artificial gravity is what they're wondering about. So is that something that we've ever, gotten close to with any spaceships? And Noah, do you see that being in the future of spaceship design, this idea of spinning to create an artificial gravity environment?
Well, I think artificial gravity is a bit of a misnomer. I mean, it's not literally a force of gravity which is occurring in those instances. But, you know, having some kind of, I guess, Earth-like gravity, trying to replicate that effect could be an important aspect. There's a lot of issues mitigating, which can be mitigated by force like gravity. For example, you know, the loss of bone, or your bones become less dense. Your organs start behaving erratically because they aren't used to just floating around all the time. So that's potentially a solution that I think is worth investigating, though I don't think we've ever had any spacecraft with humans aboard which have attempted to spin like that in order to replicate gravity.
Gotcha. Thank you so much. And so I do have some questions pouring in here on relativity and time dilation. So with that, I'm going to transition to talking to Dr. Chris Harada to help us answer some of those questions. And Chris, I do have here in my notes the words "embarrass Chris," and I've written that as a shorthand for myself to do a little brag about you to the audience, because I know you're too modest to do it yourself. I did think our viewers might be interested in knowing that Dr. Harada has one of the highest IQs ever recorded in history. And if you'd like to learn more, there's a wealth of online articles where you can go read about all these amazing things and how he's one of the most intelligent people who's ever lived. So Chris, no pressure. Super casual lead-in, but I'm wondering if you can help us learn a little bit more about this wacky time dilation stuff that's happening. It seems to have a lot to do with relativity, so maybe we should just start there. What is relativity, and what do we need to know about it as a viewer to understand this film?
Sure. So relativity, I think, actually has quite old origins. We've learned over actually centuries ago that if you are moving, if you're in a train going along at a constant speed, for example, that you experience physics the same way someone sitting still does. You can be on the train, you can pour a cup of coffee, and as long as it keeps going, same speed, same direction, doesn't hit any bumps, the coffee will pour the same way it does in your kitchen. So that idea, of course, has been around a long time. But when we start thinking about things going close to the speed of light, light is, of course, it's a manifestation of physics. It's an electromagnetic wave, a wave with electric and magnetic fields, and it too is described by the laws of physics. And so you could ask yourself the question: if you were to go even at the speed of light, if you could catch up to a light wave and ride alongside it, what would you experience? And so the theory of special relativity, the first of the two theories, addresses what happens when objects move close to the speed of light, and it does so with what seems a really, really weird idea to us. Which is that the notion of time that we think of as being the same for everyone actually is not. Just like you could go back to your high school geometry classes and learn about your x and axes, and what's x and y for you might be, what's x for you might be y for me if we orient our pieces of paper differently. And so the special theory of relativity addresses this issue of what happens when you go close to the speed of light by allowing time to work the same way. So lengths of objects, durations of time actually get, we say, transformed into each other. They're not experienced the same way by everyone. And even though no person has ever gotten in a spaceship and gone close to the speed of light, we know from experiments with subatomic particles that is in fact correct. That time can be dilated. That something going very, very close to the speed of light might experience a fraction of a second, but for us sitting in the lab, that could be minutes or hours.
One of the things,
The general theory of relativity, oh, go ahead.
I was just about to ask you about that. So you're on it. Yeah. I was going to say, in addition to it being about speed, it seems to be, a big part of the movie is how mass and gravity is distorting time. And I have a question here from Pam who says, why is it that more gravity equals slower time? So could you explain that to us?
Sure. So the general theory of relativity arose from attempts to understand how gravity works in the context of relativity. And so you might think, for example, so we know, for example, that bluer light, shorter wavelengths, have more energy than redder light or longer wavelengths. So if I'm sitting here in a room with gravity, which I am, and I shine some light up to the ceiling, and it's blue light, then that light is just a little bit redder when it gets to the ceiling because it has lost some energy as it goes up and works against gravity. And so what that means, though, is that the light that's a little bit redder has a slightly longer wavelength and a slightly longer period. Each crest of the light wave coming by, the spacing of those is a little bit longer. That means that time is measured up there on the ceiling, and the time that I would measure down here on the floor with the clock actually go at slightly different rates. And this too has been measured in the laboratory. If you want to measure it on Earth, you need a very, very accurate clock, but it has been measured. And in the case of something with extreme gravity, like a black hole, that could be a much, much more extreme effect where it would be noticeable to us if we were there.
Interesting, thank you. And so another similar question I have for you is on the black hole planet, the crew experiences these tidal waves, that seem to be an effect from this wacky gravity. And I'm wondering, would that really be possible? Could the gravity of a black hole actually affect the world, its world in this way?
Yes. So tides on the Earth are caused by the gravity of the moon, and to a slightly lesser extent the sun, pulling on our oceans and moving the water around. So if instead of the moon you had something either closer or much more massive, or both, then you could get much larger tides. So I think that is entirely realistic, and we've even seen some examples of what we call tidal disruption events, where a star gets too close to a black hole, and the tides from the black hole are so extreme that they actually shred the star. They can pull gas out of a star.
Wow.
So that aspect is I think absolutely realistic.
Amazing, thank you. So we do have about 20 minutes left, so I'm going to dedicate the rest of our time to an open Q&A panel for all our panelists. And I have now enabled upvoting for questions. So if there's a question that you really want to have answered, you can vote on other people's questions, and I'll take that into account when we're picking which ones to ask. So I think just the most pressing one that I really see is about the kitty's name. That just, that seems really important to the science of this conversation. So Dr. Lopez, could you weigh in on that for us?
Yes, this is Slinky, and Slinky had surgery recently, so that's why he's wearing a t-shirt, if you wondered why he had a tire on. So yeah, and he likes to sit on my lap if I talk, so he tends to come during events and lectures and presentations.
Well, now that we've dealt with that serious business, we can get to the fun stuff. So thank you. So we have a lot of black hole questions here. So the first one I'll go to is, do accreting black holes always emit jets? I don't see jets in the image of a black hole. So maybe Dr. Mathur, could you field that one for us? And I believe you're muted at the moment, so you might have to unmute for us.
I think Professor Lopez or Hirata might be a better person to answer that question. Laura, would you know something about this?
Sure, yeah. Hold on, losing Slinky. Okay. So the magnetic fields that are in the accretion disk, the material that's orbiting the black hole, sometimes they can direct material out of that accretion disk and launch these jets. And so some fraction of the gas that's in that disk around the black hole is actually going to be launched perpendicular and end up with these very high speed jets that are going off like really far away from the black hole. And I think it's something like 10% of the mass of the accretion disk, the gas around the black hole, is what goes into the jets.
Thank you. And then another question we have here from Chris is, do the gravitational waves detected by LIGO indicate that space can be folded? Or is that pushing the science too far? So the question again is going back to this concept that we have gravitational waves that seems an awful lot like space folding. Laura, like you described, when we talked about that pencil through the paper. So does that, in any way show us that space can be folded, or is that too much of a stretch? So that's an open question, perhaps for Dr. Lopez, Dr. Harada, or Dr. Mathur, whichever one of you would like to respond to Chris's question.
Sure. So the gravitational wave seen by LIGO, which is an instrument that accurately measures the distances between objects that are suspended in vacuum. Those are waves. They're stretching and squeezing of space and time, and those are little waves. We don't notice them. They're too weak. But those come to us from events in the universe, such as the mergers of neutron stars or black holes or other things that have a lot of gravity, would create a huge distortion in space. And also, if it's two of them together orbiting around, then they can create a disturbance that propagates out instead of just sitting there like a single star or a single black hole. So definitely that's showing you that space can be stretched and squeezed and that there can be waves on it. It's that by itself is not showing us space being folded. So I think it's still an open question whether that is actually folding space as opposed to just bending it is something that we could ever see or maybe in the very distant future imagine doing ourselves.
Amazing, thank you. And I do see here we have, on a similar note, Adrian clarified for us about A Wrinkle in Time. She was referring to a theory that 2 points in space and time could be pulled together for quicker travel rather than stretched out like the folding of the paper. So that's kind of a similar concept that it sounds like was explored in that fiction. So I have a climate question here for Jason. David mentions that one of the concerns about climate change is the impact of the thawing of the permafrost in Siberia, Iceland, Greenland. That this could be due to large amounts of methane that might be released. Is this something that's a concern to climate change scientists?
Yeah, I think it's a big area of concern, but it's maybe not understood as well as we'd like it to be. The Arctic specifically is warmed 4 to 5 degrees Celsius already. And there's an amplifying effect that as you get a lot of these sea ice, a whiter surface or snow, and it ends up melting and thawing, and you have a darker surface there that absorbs more sunlight, so it feeds back on itself. In a lot of the international reports, like the IPCC, it's a big concern, but the IPCC likes to have things with high confidence, and so it's maybe not fully captured in that because there's a lot of uncertainty, and it's an area that needs to be studied more. Methane is a potent greenhouse gas, many times more potent than CO2, And when it breaks down naturally, it ends up becoming CO2. So then it has a long residence time and stays in the atmosphere for a long period of time. So methane's a big area of concern, whether it's coming from permafrost melting or from off-gassing due to natural gas extraction.
Amazing. Thank you so much for sharing that. We have a question here from Adrian about the multiverse. Is the idea of a multiverse the same idea as parallel universes? Are those the same concepts? Dr. Mathur, would you like to weigh in?
Yes, I think the idea of the multiverse basically goes down to the fact that in quantum mechanics, nothing is certain. You can have some probability for something and some probability for something else. So as the evolution proceeds, things just keep splitting into more pieces. X could happen or Y could happen, but if X has happened, then it could be X1 or X2 after that, and so on. So the actual, what we call the wave function of the universe, just keeps breaking up into lots and lots of different parts. And people somehow find this very confusing. And in fact, it is, because if the whole universe splits into all these branches, then which branch do we see and which branch do we live in? And can we ever actually end up seeing the other branch and seeing interesting phenomena coming from there? And it's very interesting that in principle, yes, you could actually interfere with some other branch. But once things are large, like we are large objects, not small quantum objects, these interferences between branches are very small. So we'll never actually end up interacting with those branches in any practical way. So we actually only see one branch. We are not actually going to see the other branches. And so that's why we don't actually have to worry about this. But the fact is there in principle. It's the same idea that underlies the Schrodinger cat, that a cat could be half dead or half alive. It looks strange, but in fact, it's perfectly correct. So it's really one of the most fascinating things that comes out of quantum theory. And it certainly underlies everything that we do with quantum theory, including quantum gravity or string theory. It just doesn't have many practical consequences because we can somehow never see the other branches, because everything is so big that any interference with those branches is very small.
And I think that actually is similar to one of the questions we got earlier on the webinar. That is kind of what we're talking about now. They say the one thing I still haven't figured out is how Cooper transmitted this data from the black hole back to his daughter through Morse codes on the watch. Did she just stare at it forever without sleeping or taking breaks? Didn't she miss a whole chunk of it in her childhood before she could figure out the code? Was Cooper sending it in a loop over and over? And if so, what would happen if Murphy missed the same section twice or 3 times in a row? How long was this message anyways? Any ideas or insights from the panel? It's a big question. Anyone wanna respond?
We always like to send data multiple times, and especially with codes, where if you miss 1 or 2 bits in the code, or actually even quite a few of them, that you can reconstruct the rest of the message. So that's actually a very interesting application of mathematics. But as someone who works with, one of my projects trying to transmit large amounts of data down from space, that branch of mathematics actually makes it possible. That said, I think in the movie, Murphy has to be very dedicated, and she is.
Those who are fans of Doug Adams, maybe it's Douglas Adams, maybe it's just the number 42, and she spends the rest of her life figuring out the question.
That very well could be. So we have a black hole question here for Dr. Lopez. Amelia wants to know, are we really able to observe objects entering a black hole? Is it true that an observer would see an object slow down to an eventual stop before entering the black hole? Dr. Lopez, can you comment?
Yeah, so that's a great question. And the answer is no, we wouldn't actually see someone or something cross the event horizon of the black hole. We would see it approach the black hole but then it would seem to kind of stop. And that's because that person approaching the black hole, their time is slowing down, and their light is getting shifted, like Chris talked about. And so eventually we're just going to see them approach the event horizon, and then they're going to wink out. We're not actually going to see them cross. So yeah, we won't see them enter the black hole.
Thank you. A question I really like here from Timothy for the whole panel is, in the end, much of the movie was really about passing on realistic hope from one generation to the next. What are the practical signs that each of you see in your own areas of expertise? And are their students picking up the baton? So this idea of passing hope to the next generation, through the research. So Noah, we haven't heard from you in a bit. So I'm wondering if this is anything that, you've witnessed in, the aerospace side, where you see, hope, being passed on to, the next generation, which you are a part of.
Yeah, absolutely. I mean, first of all, rockets are cool, right? So that's always great at inspiring younger people to get into STEM and aerospace engineering and other related fields. The whole aerospace industry, it really needs to be looked at in more than just a technical aspect of it. You really should consider the historical context of everything that's occurred so far. Aerospace and space exploration is really storied. And so this whole idea of like inspiring the human element and this desire to be pioneers and explorers, it's truly powerful. And often if you look at NASA and the missions that they do, the ones that get the most attention, the ones that are highlighted the most are those that have humans involved, that are on the spacecraft going somewhere. So, I guess to answer the question, what are the practical signs that I see in my own area of expertise of more students picking up the baton is really like, there's a lot more to do in space. We've barely scratched the surface. The industry's only as old as approximately the 1940s. So we're just at the beginning and just the cusp of getting into space exploration. So now's a good time to get into it.
Amazing. Thank you so much. I couldn't agree more. I love that answer. I'm going to go to a new question here from Dina, who asks, is string theory saying that there are more than 3 dimensions of space and fourth of time, and time is the fourth? Therefore, going to the past could be possible if string theory is proven to be correct? ? Anyone want to respond to this question on string theory and how it could be related to time travel?
Okay, maybe I'll say something about that. It is certainly true that string theory actually has 9 space dimensions and 1 time dimension. However, the idea that Kip Thorne uses in this movie, that once you have extra dimensions, you can go back in time, that is not an obvious fact. So if you can stretch it to be true. The usual barriers to such things are the following. Even the idea of a wormhole which you can keep open. In principle, it looks like a nice picture. Once you can bend space and time to make gravitational waves, why can't you bend it more to make any other shape? So maybe a wormhole. But there's a very interesting theorem that as long as the energy of everything is positive, you actually cannot hold a wormhole open. So you can actually prove that. And that's basically because everything has positive energy. Energy is mass, so E equals mc squared if you like, and mass, positive mass attracts. So a wormhole tries to pinch and close itself. So it can't stay open unless you have some source of negative energy. Okay, now we don't actually see anything with negative energy around us. So you might say, you already can't do this. And the same also applies to making time travel. If I give you negative energy stuff, you can actually make loops which have what are called closed time-like curves. But as long as energy is positive, these things are not possible to do. So then you would say, hey, doesn't that mean you can't do them? And it's interesting, with quantum mechanics, it turns out overall energy has to be positive, but in some region it could be negative, and some other region it could be more positive than the negative, so that overall it's positive. Okay, so people have actually tried to use this to put the negative part inside a wormhole and try to keep it open. Okay, so then using this, you could also try to make time travel possible. But these are a little bit of things which I would call a stretch. I haven't actually convinced myself that a wormhole can stay open. Personally, if you ask me, I would say even to what we know with string theory, it's probably not true. But you can't rule it out. And so I think it's interesting. If you want to know more about wormholes and what can be done with it, there's another book by Kip Thorne, which I once picked up in a store. It's called Black Holes and Time Warps. And he actually spent quite some time in talking about wormholes and time travel. And the last chapter of this book is about wormholes and time travel. So it's written at a popular level. And if anybody's interested, they should take a look at that.
Amazing. Thank you so much. I think that's a great suggestion for our viewers. And in fact, you prompted another question here from Chris, who says, kind of as you mentioned, gravity and its arrow of action seems to be linked to time in the theory of relativity. And Kip seems to equate gravity control to time control. So does the panel have any thoughts on the possibilities of manipulating time through gravity? So does anyone else have any thoughts they'd like to share on this concept that Dr. Mathur was touching on?
I think one thing that I've learned from the book that Samir suggested is that Kip Thorne believes that if wormholes exist, then time travel is possible. So there is that interconnection between those things, and it is kind of fun to think about. So that's what I would contribute for that question.
Thank you. We have another one here from Samir, who says, what is the most outrageous idea that was proposed in this movie? So what is the most outrageous thing you saw in the movie? Jason, anything from a climate perspective that really struck you as an outrageous thing, or did it all seem, grounded in real life?
I mean, it seemed plausible. I think, a situation where things are dire. It was interesting how you didn't see a lot outside the immediate realm of that community, but you assumed other communities were facing the same issue. And it was alluded to in the question that there had been some world war or some reckoning event that had happened, that people had come together, but things were still kind of uncertain. No, so I mean, what was depicted was obviously a dystopian future, but seemed plausible.
Right. Any other comments from any of the other panelists on, in your opinion, what was the, least realistic part of this movie?
I think I have something to add. So one of the really exciting parts of the movie was when Cooper was flying his spacecraft up to dock with the Endurance, and they're both spinning, had to like match the momentum and all that kind of crazy stuff. And it only took a few seconds to do, right? Like no big deal. But, speaking from a more practical perspective, that's something that's really tricky to do. You need a lot of precision and a lot of accuracy. And I don't think that's something that a human pilot would be able to accomplish so quickly and so easily. The SpaceX, the latest technology innovation that we have is we have the Dragon capsule, which delivers astronauts to the ISS. And I use the word deliver kind of deliberate in this sense because really the spacecraft is entirely autonomous. The actual docking procedure to get attached to the space station is entirely performed by the flight computer. And so this idea of, Cooper just flying his spacecraft willy-nilly just wherever he wants with a little regard to the actual maneuverability and these kind of orbital maneuvers that are conventional for everything that we understand in space is, I think I would classify that as a little bit outrageous.
I think that's a really great point. Thank you. And we are almost at the end here, so I'm going to pick one final question, which is, what strange space phenomenon would you include if you were to write a movie? I think that one's a fun one to end on. So panelists, if you were directing your very own sci-fi flick, what are you featuring in your movie? Let's start with Dr. Harada.
So I think even though I study the universe, I really also like all of the things in it, and I like planets, and so I would have stuck in there some of the amazing special effects that you can get from planetary atmospheres as well. and I would have given them equal attention to the really awesome stuff you can do with general relativity.
Awesome, thank you. Any other panelists who would like to weigh in on that question? Open floor.
I think building on what Chris said is I would kind of like to see different representations of like the different kind of exoplanets that are found, that, you know, like super Earths, and what it would be like to live there, and what could grow there, and, you know, how life would be different if you had, you know, something that is 2 times the mass of the Earth or something like that. I think that'd be fun to explore in a sci-fi movie.
Awesome, thank you. And Dr. Mathur, I saw you unmuted yourself. Did you have an answer to share as well?
Something I find very fascinating these days, I'm trying to learn more about it, are all these ideas of dark matter and dark energy. And somehow that really hasn't found a place in science fiction because people maybe don't know what to do with it. But dark energy is really fun because it has negative pressure. And once you start putting in things which have negative pressure and so on, maybe you can do quite fascinating things with it. The other thing which amazes me very much is this idea in cosmology, that you can just nucleate a universe from nothing. So people say, how did our universe begin? And there's all this idea that by quantum effects, from nothing, you can actually just give rise to something, and then it just keeps increasing by inflating. It just comes up and just starts exploding. So some of the facts of cosmology are some of the most bizarre and extreme things I've learned about in physics. And maybe somebody should capture them and push them into a movie.
I love it. Well, if you have any movie makers in the audience, I think we've got a lot of good ideas for you here. So feel free to run with them. Unfortunately, that is the end of our hour. So I want to thank you all so much for joining us today. I know I learned a lot, and I hope you did too. If you'd like to join us next month, I do want to make a quick announcement that we're having our event on December 9th. So we've moved up the event because of the holiday season. And on Wednesday, December 9th, we'll be having a panel on the film Hidden Figures. So if you'd like to learn more about Hidden Figures and its history, I hope you join us next month on December 9th. So panelists, thank you so much for being here with me this evening. And I hope everyone has a great rest of their night. Thank you for joining me.
Thank you.
Thank you for
Anna.
inviting us.
Thanks for having me.
Bye. Thank you for the great questions, audience.
Yes, thank you, audience, as always, for impressing us with your wonderful questions. Take care, everyone.
Have a good evening,
Bye.
everybody.